Okay, so this is one of the most transparent models among all the models that you have looked at. Okay, and it is definitely one of the models that you should always have in your toolkit. All right. So maybe for those who are, I think maybe a lot of you are already familiar with at least the model. But for those who are maybe seeing this for the first time, so I'll just quickly show you how the model looks like. So basically, if you have, this is an example. So suppose you have some situation where you need to do product recommendation, right? So, okay, so this is something like targeted advertising, right? So maybe you have, say, you must, for example, if you are recommending a product like entertainment, right? Games, computer games, then you may actually split your customers to, let's say, according to age, right? So for those who are 24 or below, and then more than 24, okay? So for those who are 24 and below, you will just recommend them like football games. Okay. So you will recommend some sort of football games to them. Okay. World Cup, UEFA, FA, things like that, right? So if they are more than 24, then maybe you can consider another variable. Let's say whether they smoke or not, right? So if they smoke, right, and these are maybe they don't smoke or you have missing values, right? So it can take in missing values, all right? So in fact, this one you may also have missing values may actually go to the right-hand side, okay? So if they smoke, then you will recommend them action games, right? Okay, those that are like shooting or punching up people and stuff like that, right? Action games. So if they don't smoke, all right, then you may have a further variable, like for example, education level. Okay, so if this is tertiary, this is maybe less than tertiary, right? Tertiary or more. Okay, so this one you will recommend to them action games also. This one you will recommend to them strategy and simulation. Okay. So this is a decision tree model, and it's not hard to see why for example, your business development manager, if you do some analysis, you come up with this model. It is quite easy to understand why they would like this model, yeah, because it immediately tells them, okay, what are the things. It basically suggests immediately, right, how they should push their products. Okay. So their salespeople would immediately, based on the model, it gives them a very practical way to target the customer, right, on a segmented on a segment of the customer population, okay, on what are the things that they should actually sell, all right, to the customers. Okay, so and if your tree is not complicated, right, this is considered a simple tree. So this is a tree, and this part here is called a node, right? Okay, this is a node. So these are what we call the leaf nodes. Or sometimes it's called a terminal, okay? This is a root node, right? The one that starts from the top is the root. So then you have leaf nodes, right? And this would be something what we call intermediate nodes. Okay. All right. So these are basically data in your. So these are your features, right? These are your features in the data set, right? And so here, this model here has 3 features are important. Okay. All right. So this is an example of a recommendation, right? So here, this will be your class. Okay. Okay. So this will be your class label. The class labels will be all occurring at the leaf nodes, yeah, the terminal nodes. Okay. So it's very transparent, and in fact, a lot of times, like for example, when doctors make diagnosis, right, the very good doctors, they basically memorize the decision tree, right, for their particular field. Like for example, if they see if they see, for example, patient has a certain condition, right? Yes, no, and then keep on like this, right? Yes, no, right? So basically, doctors, they love decision trees because that's how they are trained, right? In fact, the very good doctors are the ones who actually can recall maybe a very complex decision tree, right? That makes them make diagnosis, yeah, because they that's why how they make a diagnosis very quickly can be a matter of life and death, right? So but sometimes you have to memorize the decision tree, yeah. Like if you see this condition, then it's this case. If you see that, okay, then you check other things. You go on and check this and that, right? And finally, you reach a decision like maybe this one is you need to. This is an emergency case. This is maybe normal case, emergency case, and so on, right? And and then you have to do this very quickly. Okay, so obviously that's why in certain disciplines like medicine, the person's memory has to be very good, right? You cannot say that, oh, okay, I vaguely recall this and let me check the book, right? Doesn't work like that. That's why in that field they need to do both things. Yeah, they need to have memorization skills, obviously, but also they need to know the science very well. Yeah, so not easy to find people who are very good in both aspects. Okay. So this is a decision tree, and this is only part of what it can actually do. It can actually do a lot of things. Okay, classification is one thing. The other big thing is it can do regression. Okay, what we call a regression tree. So to see why a regression tree would be better than your traditional regression, so I'll show you an example here. Okay, suppose you have your you have a data set like this. Okay, so this is your X, this is your Y, right? Okay, so if you do global regression, right, what are you going to get? So that means you do a global regression model. Will this actually work?
No.
That means you try to fit a straight line across this entire data space. Will you get a good model?
No.
What? Is there, I mean, if you just look at it visually, right? Can you fit a linear equation through this data space and then get a good fit for your data?
No.
No, right? Impossible, right? But how could you still use the idea of a linear model and then get good fits?
separate into some other regions.
Okay, great. So the idea is to actually look at find splits, right? So let's say, so you notice that, okay, if you fit one global model, it probably doesn't work. But it seems like the linear model will work if you look at certain partitions, right? That we call partitions. You look at certain partitions of the variable space. Okay. So, for example, if you make the partitions here, right? And this is let's say node 1, this is node 2, right? So in this partition, then it's clear that this regression line here can minimize your sum of squared residuals. And then there's another model that's going like this. And over here, this will be a flat line, right? So, so this is the idea of the regression tree. So the regression tree basically is basically still doing regression, but is doing the regression in certain data partition, in certain partitions of your variable space. Yeah, it doesn't try to do it do one model globally. Okay, because usually for complicated phenomenon, you are almost sure that a global model will not work, right? And you need to work with data partitions of the space. So then if you have a partition like this, then you will be able to do very well your model. So the first one will be you split, the first split will be maybe here. So this is node, maybe I'll call it node 1. Okay, this will be the left side, right? So this one maybe some value A, this is some value B, right? So suppose your X is less than or equals to A, right? So it will go to this space, yeah? So in this space, your model will be, let's say, so that will be your model, right? Okay, so that will be your model. And if your X is larger than A, so it will be going into use the spotlight. So this region, right? So you'll be using this region, okay? And for this region, you will actually, okay, so X greater than A is actually this, in fact, is actually this entire region, right? So you can basically then consider another split here, right? N2, right? So if you're, for the second node split here, if the X is below or equals to B, and then X greater than B, right? So for X greater than B, it will be this region, right? And for X less than B, it will be actually this region, okay? So in that case, here your model will be, so if you fit this model in this space, okay, it will work very well. And over here, the model here is basically a constant line, right? Okay, so this is a regression tree, and nothing complicated, nothing unusual. It's still using regression, but your regression is basically applied on different partitions of your variable space. Okay, in fact, you can actually do on certain partitions. You can then have your multiple regression, right? But the advantage of the regression tree is that you can find certain partitions in such a way that at the end, right, towards the end, you can just use a simple linear model, right, to explain the relationship between your response and a significant predictor. Okay, that makes your model also very transparent, right, and easy to understand. Simple linear models are the easiest to understand, right? And in fact, instead of so regression is totally general, right? So instead of linear models, you can also consider polynomial models, right? So over here, you can actually set the regression here to be a polynomial model if you want to. Okay, there are many possibilities. Okay, and you can even set it to be a logistic regression if your response here is binary. Okay, So there are many possibilities, right? So now I think by now you realize that basically the idea is to look for partitions, right? Okay, partitions. And so let's look at another example. So you have, let's say, so you have, let's say, data that's like this. And also, let's say you have data that's like this. Okay. So you can basically classify the data as being circle or plus, right? Two types. Using the following partitions, right? So the first thing you might actually partition, maybe you'll make a partition here. Okay, so this is x1, this is x2, right? Okay, so anything that is, so this is node 1, right? So node 1, if your x2 is above, let's say, some value 10 here, x2 is, if x2 is less, more than 10, so you will classify it as plus. Right? Otherwise, if it's less than or equals to 10, then it will come to this part here, this region. And then you will partition, like, let's say you have a partition here. Okay, let's say this is 5. Okay. So then you will have node 2. Yeah, this is node, this partition is node 2. This partition here is node 1. Okay. So in node 2, anything that is less than, for x1, anything that is less than or equals to 5, you will classify as plus. And if it's your x1 is more than 5, so you are looking at this space here, then you make another partition, let's say here. So this will be your node 3. So this is maybe, let's say, 10. So if your x1 is more than 10, then you will classify as plus. And if it is less than or equals to 10, it will be classified as circle, right? So basically, you can see that with repeated partitions of your variable space, you basically get the tree, right? So your tree is basically this tree representation here. This entire tree model basically corresponds to a partition, right, in your variable space. Okay. Now, of course, here I to simplify the matter, I only use 2 variables. Okay. But in fact, you can have multiple variables like x1, x2, x3. Right. When you have x1, x2, x3, basically the situation is like this. So you basically have a plane like this, and it's just let's say this is a plane x1 against, so x1 against x2. This is x1 against x3, or something else. So suppose you have some variables like this. Okay, they may not be separable in this space. It doesn't matter, right? Let's say you have some that are separable. Okay, so it doesn't matter. So in this case here, I can have a partition. Let's say I partition in along x1 here. So this is my node 1. My x1, if let's say this value is 10. So x1 less than or equals to 10, okay. Let's see. Okay. Maybe let me try like this. Okay, maybe let me put the partition somewhere around here. Okay, this is 10. So with this partition, this group, they are all plus, okay? So let's say now your X is, this one is larger than 10, right? So it will include this group, okay? Now, you see that here there's a mixture, right? Okay, so it doesn't matter. So let's say we consider another space, right? Let's say we move to another space. Let's say in this space, this part here, they are well separated. Okay, in this space, let's say you will have, let's say, it separates on X3, okay? Actually, my notation is a bit weird. So, circle. And the circle here is maybe sort of like, so X1 is here, they are mapping, but let's say they map like this. Okay. Yeah. So over here, so basically now you're switching the plane, you're switching the space, right? From this X1, X2 space, you go to X1, X3 space, right? And over here, you'll find that you can get a decent partition. Okay, you can partition along here. Okay, so this will be node 2, and you are partitioning on X1, right? So if X1 is, let's say this is like say this is 20. If X1 is more than 20, then you will classify as circle, right? If not, so if it's on X1 that is less than or equals to 20, so it's here. So you need to find another partition along here, okay? So that will be, you have another node 3, okay? So this is node 3. So this is node 2. Here it is node 1, right? So your 3, you will partition along X3, right? So this is X3 greater than, let's say this is 5. This is X3 less than or equals to 5, okay? So this will be a plus, okay? And this will be a circle. All right. So in this case, you can see that variable x1 is used, variable x, well, here actually variable x1 and 3, right? It's moving x1 and x3. But actually, it's also possible that maybe over here you first partition out this space. Okay, so that's another model, right? You partition out these bits here. They maybe you have something. So instead of going to 1 and 3, right? This space, you first partition out this space, and then you classify as the red, and only all those here you consider them in the x1, x3 space. That's also possible. Okay, so basically your algorithm is moving through different spaces, right? It can move to different spaces and then find the partitions, right? Okay, so this is the general idea. Okay, now the question is, how does it actually prioritize, right? So now that we know that, okay, so this is basically the idea, right? That you make partitions in the variable space. There are two questions here, right? So questions how? Okay, how to choose variables to make splits. Okay, that means make this kind of splits. So this is actually a variable selection problem. All right. So in fact, when you give variables to a decision tree, it implicitly does the variable selection. All right. So implicitly does variable selection for you. Okay. So in fact, if you didn't do any variable selection, some kind of pre-processing, right? Variable selection is also fine. It will do it for you, right? Because it's implicit in the model. Then after that is how to determine splitting point. Okay. Once you determine which space to split, then you have to determine the splitting point, right? The question is, why do you split in this line? Why don't you split here or here or here, right? How do you decide, right? Whether you split at this point and not at other points, okay? Like why split here and not split in other points? Okay, so these are the two questions. Okay. Now, before we go to this part here, how they do this part. So one advantage of using the classification and regression tree is that you don't actually have to the data types. Yeah, your data types. You can use them as they are. Okay, the categorical. It's okay. Numerical, okay. Missing values, also okay. Okay, you don't have to impute missing values, no imputation. Okay, it will treat missing values, like for example over here, if you have missing values, it may actually go to either one of these nodes, right? For example, NA may actually go inside here. So you don't need to do imputation, and that's a huge advantage, right? Because all the other methods that you learned so far, yeah, like naive Bayes, neural networks, okay, all those things, you have to do imputation. Otherwise, the algorithm will just get rid of those rows with missing values. Okay, and this is I think one of the main very big advantage that decision trees have on all the other kinds of algorithms. If you happen to have a lot of missing values, okay, because when you do imputation, right? Imputation is basically you make guesses, right? Make guesses. And you make guesses, when you make guesses on the missing values, you have to make certain assumptions about the mechanism of the missingness. And usually people will make assumptions about missing at random, okay? Because otherwise there are too many possibilities, right? Why the certain values are missing. So, but then most of the time, a lot of the missing values are not because of randomness, right? They are missing because certain kinds of response tend to be missing, okay? Like for example, if when people choose not to reply you, right? When you ask them about a certain statement that may be sensitive, right? They may actually have chosen not to reply to you because they know that the answer they are going to give an unpopular answer, right? And they are afraid that that unpopular answer may expose them to some kind of consequences, okay? The fact that they choose not to answer you, in fact, says a lot about their opinions, actually, okay? So in fact, the missingness is actually a kind of information, all right? And when you impute them using some other things, you are kind of like introducing potential noise into analysis, okay? So this is one of the good things about regression decision trees. They do not actually, you don't actually need to make imputations on the explanatory mode. On the explanatory predictor variables, no imputation needed, right? Okay, so of course in your response variables, must not be missing. If your response variable is missing, then you have to throw that variable away, right? Because you don't know what is the outcome, okay? And that is that is not in the realm of supervised learning. Okay. So these are this part, it is very strong. Okay. Doesn't need to do imputation and can handle missing values. Okay, and just handle the numerical and categorical variables as they are. If you use neural network, right, and you happen to have a lot of categorical variables, then you have to first transform, yeah, the categorical variables, okay, into using something called the log of odds. Log of odds ratio to convert categorical values to some kind of a numerical value. Okay. So that step, if you don't do it, then you can get a lot of errors, yeah, in your model, right? If you feed categorical levels and treat them as numerical data in artificial neural network, for example, you are going to get a faulty model, okay? Because they are not strictly computable, right? The categorical levels, they are not sitting in the Euclidean space. So you got to transform them to a Euclidean space first, right? It's just like working with compositional data, yeah? They are in a simplex space, and you have to bring them to the Euclidean space first before you can actually treat them as a standard input in those kind of standard methods, right? Like naive Bayes, like artificial neural network, like linear discriminant analysis, and so on. Okay. But then for regression trees, you don't have this problem. All right. So these are already like some very big incentives to use them. Okay. Now, so let's look at the ideas. Yeah. How to make the states. Okay. Now, first thing to note is that although you have this thing called classification and regression trees, there are actually three main algorithms. Okay, their implementation, because this part here, there are different ways of doing implementation. So I'll just briefly explain what are these three. One is called CART. CART is basically just a short form for classification and regression trees, right? The other is something called C5.0. Okay, and then the other one is called guide. Okay, so so all these, they are kind of like different algorithms to do CART. Okay, and then in R package, there's something called RPart. Okay, RPart is basically a R implementation of CART. CART still has a commercial software which you have to buy, but it's already very old. Yeah, this CART is like a is like a very ancient software. It has not been updated for, I think, for many years, all right? But then it's still sold as a commercial product. Okay, so this is kind of like very ancient. There's some R packages to do that. It's called RPart, and then that is also C5.0 is also it's popular among comp science people. Okay, comp science, and then there's also a C5.0 R package. Okay, that's available, which you can do. Then this is guide, right? So guide is actually made by a statistician. It's made by a statistician, right? And so far, right, all among these three programs, the best one is this one. Okay, is guide, yeah. So don't use this tool. Okay, use this one. You will get different, even if you're the same input, you will get different control parameters and different outputs. Yeah, if you use data sets that are sufficiently complex. Okay, guide will give you trees that are the best ones. Okay, there's so the person who did guide has done a lot of studies, right? Last year, I think in 2019, he was here to do a workshop, right? So we invited him to come over. So he has done many years of research into this kind of model, and he found out that CAT and C5.0, they tend to produce what we call bias trees. Okay, so he found that these trees, right, if you use these programs to make, they have a major problem, right? And first they have the problem of bias towards variables with many categories, right? So if you have a variable that has, let's say, 10 categories, okay? Regardless of whether this variable is useful or not, yeah, informative or not, CAD will get tricked to pick this variable as one of the nodes, okay, in its model, right? It's just sensitive to the number of categories. And then there's also a kind of bias towards predictors with more missing values, okay? So he has also found that this either CAT or C5.0, it will have a bias towards, if you have a predictor that has a lot of missing values, then that predictor will get picked almost always, right, into the model. Whether the predictor is useful or not doesn't matter. It just gets picked simply because it has more missing values. Okay, and of course that will create a bias. All right, and then the other thing is these two programs will break when you have some explanatory variables and that have a number of categories greater than 32. Okay, this is just basically a consequence of how they actually grow their trees. Yeah. Okay, so these two things are actually these two programs. They are still, a lot of people still use them. Yeah, it's more like a situation of they are not aware of this guide program, right? So now that we are aware, so please learn how to use it, right? So this program is very it's actually not hard to use, right? But you have to prepare certain input files first before you can actually run it. But once you know how to do it, it's actually very easy to do, right? Okay, so okay, this is the just the software aspect, right? Okay, which program to use. So later we are going to do some examples with this software. Okay. I think last semester, for those who studied the class, the consultancy course, you already have been exposed to it, right? But it's okay. We look at it again and see how to use it for other kinds of situations. Okay, so now I'm going to explain how the first thing I explain how the split is chosen. Okay, how? Okay, so basically, let's say you have your data like this. 1, 2, 3, 4, 5. Okay, so I got 5 points there. Then I got 5 points here. 3, 4, 5. Okay. So here I want to introduce the idea of it's a measure called Gini. It's something called Gini impurity measure. Okay. So this basically is a measure as follows. So G is equal to pi times 1 minus pi, then you sum over the I. So the I is the index for the class. Okay, so if you look at this form carefully, you'll know that this looks very familiar. This is like your binomial variance. Okay, it looks like a binomial variance, yeah? And if the number of classes is equal to 2, yeah? Then basically your Gini impurity is basically just 2p 1 minus p, yeah? Okay. If you only have 2 classes, then your p1 p1 is equal to 1 minus p2, right? And so therefore p1 1 minus p1 is the same as p2 1 minus p2, right? Because this part will be here, this part will be here, right? So you sum, you get 2, right? Okay. But otherwise, it is just this, okay? So it's very easy to remember. Yeah, Gini impurity is basically a binomial variance kind of sum, right? Summing over all the classes. Okay. Now, so before we make the split, right? So we have a Gini impurity of let's say we say before G before, right? So G before means everything, right? So you look at everything here. The proportion of plus, right, is 0.5, correct? And then the proportion of minus is also 0.5, right? So we have, so, okay, never mind. We look at the plus first. So plus, so the proportion is 0.5, then you multiply by 1 minus 0.5, okay? Then you add, so proportion for minus is 0.5 multiplied by 1 minus 0.5, okay? So basically you get 0.5. Right? This is before you make any splits. Okay. Now, suppose now you make a split. Let's say you split. If you split, so the obvious split is you split somewhere around here. Okay. So you make a split over here. Then this part will be the left part. This will be the right part, right? So the Gini on the left part. GL, right? The Gini impurity on the left part will be, so on the left part here, you only have everything plus, right? So the proportion of plus is 1. So 1 minus 1, you get 0, right? So you add, so the other class is 0, right? So the proportion of minus is 0, 1 minus 0. So you basically get 0. Okay? So the Gini impurity measure on the left side is 0 because they all consist of one type, right? There's nothing mixed up. So the impurity is 0. Okay, that's easy to understand. The same with the right-hand side, right? The Gini impurity on the right-hand side is equal to 1, 2, 3, 4, 5. So again, these are all the same type, right? So you have, so for the plus is 0, 1 minus 0, plus 1 times 1 minus 1. So you still get 0, okay? And then finally, you have the Gini index, right? The Gini index is basically you have the left and right, okay? Well, actually, I don't need this, okay? At the end, I just need to know, right? The gain, the Gini gain, okay? So the Gini gain is basically the Gini index before subtract the weighted form, yeah, the weighted form of your left and right. Okay, so the weighted form here is to give the evidence, yeah. So if your left-hand side has got more data points, then of course you should have a greater weight on it, right? Because the evidence is stronger, right? So basically, it is just adding a weight there that is looking at what is the proportion of data points that get to the left-hand side, okay? So over here, your Gini before you have calculated at 0.5 minus. So since you have 5, right? 5 on the left, 5 on the right. So the out of total 10, so it's 0.5 times 0. Okay, the Gini impurity on the left is 0, and plus 0.5 times 0. Okay. Okay, so the Gini gain is 0.5, right? This is a large gain, yeah? You see that before your Gini impurity is 0.5. After you make this split, your impurity is 0. So you have a gain of 0.5, right? Which is basically everything, right? Before you have already lost all the impurities that you have at the beginning with this split. Okay? So this is the, in this case, you have the Gini gain of 0.5, yeah. So is it so far so good, everyone? Is it okay to follow this calculation here?
Yes. Yes.
Okay, then okay, so I think it's actually quite straightforward. Right? So anyway, now if I make the split, okay, so I want to show you the difference. Yeah, what if you had made a split like the following? Suppose you didn't split here, but you split like over here. Say you split you split like this. Okay, if you pick this split here, so this is your left, this is your right, right? So the Gini on the left now, so left everything is plus, right? So its impurity is 0, okay? The Gini impurity on the left is 0, so we don't have to go through that calculation anymore. But the Gini impurity on the right, now you see is not 0, right? Because you got 1 plus here, okay? So this is, how many points are here? So 6, right? So 1 out of 6 times 1 minus 1 out of 6, right? And plus the remaining one is the minus. So how many of them there? 5 out of 6, right? Then multiply by 1 minus 5 out of 6. So basically, of course, this is 1 over 6 times 5 over 6 times 2. Okay? So this will give you 3, so 5 over 18. Okay? So then you calculate your gain, right? The Gini gain is 0.5, right? Here, subtract the weighted form, right? So how many points are there on the left? There are 4 points, right? 4 out of 10, okay? Get split to the left. Then multiply by the Gini impurity, 0. Plus there are 6 here, so 6 out of 10. Multiply by the Gini impurity, 5 out of 18. So you get 0.5 subtract, this is 0. So this is 3, this is 2. So minus 1 over 6. 1 over 6 is half of 1/3, right? So this is about 0.17. So this is about 0.33. Okay. So here your Gini gain is only 0.33. Right, whereas in the beginning, if you had split here, your Gini gain would have been 0.5. Okay, so the algorithm will pick. So the algorithm will pick the split. So there might be. So it actually will search through maybe certain intervals. Yeah. So it has a. So basically, it will divide your axis here to certain number of intervals. Then it will check one by one. Okay. So the algorithm will pick the split S here, right? The split that maximizes the Gini gain. Okay. So at different splits, you will get different Gini gain values. It will find a split that maximizes it, right? So therefore, it makes sense that it will find this split. Okay. So at the end, it will give you this value, right? This is how it finds it. Okay, using Gini impurity measure. This is just a very simple measure, right? And it already works quite well. Some other algorithms, they may actually use another impurity measure called entropy, which is actually kind of like similar, okay? It's just instead of this formula, you have the Shannon entropy. So it's given by H equals to the sum of minus this I is also class, but you have pi times log base 2 of pi. Okay, so it just instead of 1 minus p, you have a log base 2 of p. Okay, and you have a minus here because well, your p is a proportion, so when you take log of proportion, it becomes negative, right? So you have to put a negative here to remove the negative sign. Okay. The calculation is the same. Okay. Again, you split and then it will calculate the entropy on the left split and the entropy on the right split, and then also it will apply this weight, right? This weight depending on how many samples go to the left and how many go to the right. Okay. It's the same, right? The calculation is the same except that you change the function, right? It's been found that so actually, Guy actually uses the Gini impurity. Okay, so so this impurity function seems to work better than the entropy. Okay. Right. Okay. So is it clear to you how the split is chosen?
Yes.
So this split here, this is for a continuous case, right? Of course, if you have categorical, is also easy to do. And let's look at the case of categorical splits. Okay, so if you have categorical, let's say you have plus, minus. So this is maybe say male and female, right? Okay, so so let's say so let's say before you split by male and female, right? Before you make a split based on male or female, you have something like this. Let's say 10, 10, 10, 10. Okay. After you split by, let's say, if you split by male, right? After you split by male, if you get something like this, on the left split, maybe, okay, let me choose something like this. So without splitting, let's say you have they're all mixed up here. Let's say you have 20 here. 20. Maybe 10, maybe let's say 0 here. right? Um, okay, maybe I think have to be like this. There's actually another variable. So maybe you have, let's say this is smoking. Yes. Smoking, no. So you usually have more males smoking. So let me change this. Maybe let's say you have 50 here. 10, 20, 0, okay? Let's say you've got 80 here, you got 20, you got maybe 10, 0, okay? So maybe you have something like this. Okay, so now let's say you split by, so let's say this is your, this is again male and female. You split by, let's say, so this is smoking. Yes, no. Okay. So if you split by male, then you split by female here, right? Okay, so let's see. If you have, you split by smoking, then how do you complete this table? Males who are smoking. Okay, males who are smoking, they are actually 30, right? And males who are not smoking, they are 20, right? So you will get smoking maybe 10 here, 20 here, then you have 20 here, right? So this one you will have this and this. Okay, so you basically have 10, 0, and 10. Okay, so if you, am I doing this correctly, the splits? Oh, okay. Okay. Maybe I should. Okay. I'm making it complicated. So it's just like this. Okay, suppose you have a table like this, right? So if you don't split, right, the Gini before will be, so let's see, so you will have the proportion who actually have, so this will be 0, 10, the class, right? Sum of pi. So the I has to be the class. Okay. So this total is 20. This is total 20. So yeah, so over here you will have, without splitting, it will be 0 0.5, 0 0.1 minus 0 0.5, and the same thing, okay? Right, okay, because the proportion of the plus is 20 out of 40, right? So 0 0.5, okay? So over here you have 0 0.5. If you make a split for the male and the female, right? So what happens is that your Gini of the left, the impurity on the left will be 10 out of 30, 1 minus 10 out of 30, plus the other one is 20 out of 30, 1 minus 20 out of 30, okay? So this will be 1/3 times 2/3 times 2. So that will be 4 out of 9, okay? And the Gini on the right is basically 0, right? Because there's no impurities, right? It's just made out of one type, one class, okay? So Gini on the right is 0. So basically your Gini gain after splitting on male and female is equal to 0.5 minus the weight, right? So the weight here 30 out of 40 times the left is actually 4 out of 9. The right is 0, okay? So you get 0.5 minus 12 over, so this is 3. So 1/3, right? Okay, minus 1/3. Right, so that is 1/2 minus 1/3, so it's 1/6. Okay, so Gini gain is like this. Actually, the Gini gain for two class is actually trivial, right? Because you know that you will just split it to male and female. Okay, so it's actually not that interesting. What's more interesting is when you have more than 2 categories, right? Let's say you have category 1, category 2, category 3, category 4. Right? So how are you going to split it? Okay, do you split on C1? Do you split on C2? Do you split on C3? Or do you split on C4? Right? So in that case, the calculation will be as such. You just extend the table, right? Instead of having 2 by 2, you extend it like this. And then you have basically the calculation will be similar. Okay. So that's the case when you have more than two categories. Okay, so that is the part about the splits, yeah. Okay, so so we have 10 minutes more, but I don't think it's enough to talk about the next thing that I want to talk. So maybe let's take a break now, yeah? Okay, let's take a break now and we come back at 8 o'clock, okay? Okay, so now I want to look at the aspect of variable selection, yeah? So variable selection in guide. Okay, guide actually has a very interesting way to do variable selection, and it's actually this way of doing variable selection is gives good results and is very fast, right? It's based on the use of the following. Okay, so suppose you have let's say suppose you have if you have categorical variables, of course, then you will do a if the variable if variable is categorical, okay, then I can find out the chi-square value of the contingency table, right? So you have the so this is your class, let's say plus minus, and these are your levels, right? So category 1, category 2, and so on, right? So then you can have a chi-square value, right, for this table. Now, of course, this chi-square value will have a degree of freedom V new here, where this is your degree of freedom. And of course, the degree of freedom is equal to the number of rows, subtract 1, times the number of columns, subtract 1, okay? So if you have different categorical variables, of course, their degrees of freedom will be different, right? So some of them may be chi-square 5 degrees of freedom, some of them maybe 1 degree of freedom, some chi-square 3 degrees of freedom, and so on, okay? So it's very hard to compare them when their degrees of freedom are different, right? And then you ask, why not use p-values, right? Why don't we calculate p-values? Now, p-values are not useful in this case for comparing between the different variables, okay, for variable selection. There are several reasons. First thing is your p-value may be very small, okay? So when you have very small p-values, then you basically have to compare values that are very small, and it's actually not clear what is going on, yeah? Suppose you have something like 0.00001, the other is 0.0000008. So it only differs by, say, 0.0000002. Okay, it differs by such a small value, and then you are going to rank this above the other variable. So it's a bit unclear, yeah. Okay. The second thing is simply because the chi-square distribution may not be accurate. Okay, for certain table structures. Okay, you know that in order for this chi-square approximation to be more or less accurate, you need one condition, which is the expected cell, right? Must be more than 5. Okay, So basically, the cells here, the expected value for a cell has to be more than 5. And when you have quite a few variables like this, it's very hard to ensure that, okay? So some of them may not have an expected value that's more than 5. So that means the distribution, yeah, okay, is actually approximate and very hard to, so you're not sure, right, whether the calculated p-value is really accurate or not, right? So this is one thing, okay? So so the creator of guide, okay, which is Professor Low, all right. So he figured out a way to standardize the chi-square values, right? He introduced a transformation called it's actually an old result, but it turns out to be useful. A result called Wilson-Hilferty transformation. Okay, so this transformation can it can convert a chi-square random variable of v degrees of freedom to a chi-square 1 random variable. Okay, so any chi-square random variable with degrees of freedom nu, after it undergoes this transformation, it will become a chi-square random variable with 1 degree of freedom. Okay, so what happens is that, so if you do the Wilson-Hilferty transformation for all these chi-square values, right, they all end up with chi-square 1 degree of freedom, right? And then you can basically just rank by chi-square. Okay, rank them by chi-square 1 degree of freedom. Just rank their values, and then you can find out which one is important. So which one is top rank and which one is not. Okay. So just briefly, I show. So the this Wilson-Hilferty transformation looks like this. Yeah. It looks like this. So this is the data x. So it's given by the max of 0 and some result like this. Okay. So you don't have to worry about this. This one is just I'm just explaining what sort of method was used to do feature selection. So apparently this method was used to convert the chi-square. Okay. So you basically you put in this value, you put in here, right? You plug in here, you compute this. Yeah, is either which one is larger. Yeah? If this turns out, if this value is negative, then it will become, you will replace it with 0. Okay, otherwise it will take this value. Okay, so basically after it goes through this transformation, it becomes a chi-square 1 random variable, and then therefore then we can compare, we can rank them, right? We can rank all variables. Okay. Then you take the top ranked, top ranked variables. All right, so this is the idea. And how about continuous variables? Okay, for categorical variables, it's easy to do the chi-square table, right? But how about continuous variables? So for continuous variables, so this is what is done is as follows. Yeah, you take the sample mean plus minus the standard deviation, okay, times square root of 3 over 2. Okay, let's start with 3 first. If if this condition is true, yeah. Okay, so this NT is the number of training samples in this terminal node, yeah, terminal node T. Well, actually, I just say node T lah. JT is the number of classes in T, right? So if this condition is true, then you will create three intervals. Okay, the intervals will look like this. So basically, you have the following. This is x bar, so you have x bar plus s square root of 3 over 3. Okay, and this is x bar minus s square root of 3 over 3. Okay, so your interval will be, there will be 3 intervals, which is so one interval here. Okay, anything that is less than this value, one interval. Anything that is more than this interval, this value, one interval, and then whatever that's in between here, one interval, right? So when you do this, then you can actually, so you will have something like this, below x bar minus s square root 3 over 3, one interval, and then this one you have x bar plus s square root of 3 over 3, right? More than that, okay? The other one is in between. Okay, so you got 3 intervals, and here is your class. Say 0, 1, right? Okay, so you see how they are distributed in this contingency table, right? And then of course you can find your chi-square value. Okay, so in this case the degree of freedom will be 2, right? Because this is 1 degree of freedom. Here there are 2 degrees of freedom. Okay, and you can calculate the chi-square value, right? Now how are missing values treated? If you have missing value, right, don't worry, you basically just create one column for it. The NA is here. This explains why decision trees never throw away missing values. The missing values are simply put inside a category of their own, all right? So it doesn't cause any trouble to the use of chi-square statistic, yeah, to do feature selection, right? So that is actually a very interesting way of retaining missing values, okay? And then otherwise, so if this condition is true, you have this. Okay, you do these 3 intervals, right? Otherwise, if the condition is larger than or equals to, then you split into 4 intervals. Okay, so the 4 intervals look like this. So you got 4 intervals, and they are like this: x bar plus minus s square root of 3 over 2. So basically, it's like this. You have x until here. Okay, so this is your x bar. So then you have okay, so this is x bar minus s square root of 3 over 2. This is x bar plus s square root of 3 over 2. Yeah, that's it. So, okay, so you have one interval here, one interval here, and one interval here, one interval here, right? So 4 intervals, 1, 2, 3, 4. So if you do the table, it will be like this. This will be less than x bar minus s square root of 3 over 2. Then over here you have x bar minus this until x bar. And Then you have X bar to, okay. And then over here is X bar, so more than X bar plus S square root of 3 over 2, okay. So here will be your class 0, 1. Okay, and then if you have NA, then you have one more column here, right? So then basically you can have your chi-square value. In this case, this chi-square value is 1, 2, 3, 4, 5, 4 degrees of freedom, okay? All right. It's the same with, so then you will have all sorts of chi-square values, right? Some of them 5 degrees freedom, some of them 1. So you basically, again, take them through the Wilson Hilferty transformation, and then they'll all become chi-square 1 degree of freedom. So then you can rank them, right? So in this sense, it has a kind of like a very beautiful statistical approach to do feature selection, right? Now this sort of method can only be devised by someone who has studied statistics, okay? Therefore, you see that these methods are novel in this program, right? They are not used in the C5.0 because this kind of ideas, if you haven't studied statistics before, it's very, you will not come across it, right? Okay, so this is one of the novelty of the feature selection step in guide that makes it very fast. Okay, so once this has been done, okay, so you have the chi-square values, and then you can basically just rank them, okay? So, okay, before that, maybe I just show you the show you the examples. Okay, can you see the slides?
Yes.
Okay. So this is an example of applying just now those criteria, right, of splitting the because you can always categorize continuous data, right? So this is the way you partition, right? So this is the classical iris data set. So you can later actually convince yourself that you can actually do some calculations and see that this, like for example, this part 2.2 here, this will be basically your X bar minus standard deviation times square root of 3 over 2, right? So you see that there are 4 intervals here, right? So basically, after you cut into intervals, and then here you have for the iris data set, you have the 3 species here, right? So then you basically just bin them, and then you can calculate the chi-square value, right? So in this case, you don't need to do, for this example, you don't need to do the Wilson-Hilferty transformation because all 4 contingency tables have the same degrees of freedom, right? So you can directly just rank them, right? So from here, you can see that petal length and petal width are have chi-square values that are very large, okay? So suggesting that these two will be useful for discrimination, right? Compared to, let's say, sample width, right? Okay? So you can see that then you have splits like that, okay? So, okay, just wanted to show you that. Let's see, then I exit. Okay. Okay, now, so I want to say something about how Guide actually does the tree, okay? So you have the full data. So what Guide does is that based on the full data, it will keep on splitting the tree. It will split the tree until some, okay? It will make splits, yeah? Until some stopping criteria is reached. Some stopping criteria are reached. Okay. So the stopping criteria may be that you may require the leaf node to be having more than, let's say, 5 observations, right? So you split until here, like if further splits, right, result in nodes that have less than 5 observations, it will terminate. Okay. So this will be the full tree, right? Now the full tree is actually we don't usually use the full tree because the problem with the full tree is that it always is overfitting. Risk of overfitting is high. Okay, so usually we don't use the full tree for as the final model, right? Because it's just so easy to overfit, right? You can just keep on growing, and then your tree will be complicated. And it may overfit and also make it hard to explain the results, okay? Especially if this keeps on expanding, right? So what happens is that in Guide, they do something that is different. So they do something called cross-validation. They create cross-validation trees. Okay, what does it mean? So basically you will, your data set, right? You basically will split in, I think we discussed the idea of cross-validation before. So you have, let's say, plus and minus, let's say binary case. If you do a 10-fold cross-validation, that means you will split into 1, 2, so it's like this. Okay, so basically then you will have, you randomly create 10 layers, yeah? So 1 layer plus minus, 1 layer plus minus, and so on, right? So basically you have 10 layers, okay? With 10 layers where you have similar kind of proportions between plus and minus, right? And then you basically withhold one of the layer. You basically maybe you hold, and then you use the rest. You use 9 layers. You use basically if you have 10-fold, you will use 9 layers to build the tree. Okay, so basically it's like you are kind of like withholding part of the data. Okay, and you build the tree using the remaining 9 layers. Okay, so this will give you some kind of tree. Okay, that is different from the tree that you get from the full data. And then you can, if you have 10-fold cross-validation, then you will have 10 trees. Okay, depending on what is deleted, all right? Okay, you get 10 trees. And then, so then you will have to, it will pick your final tree from among these 10 trees, yeah? So the cross-validated trees, okay? you can pick the final tree that will be reported will be picked from here based on the KSE rule. Okay, so this SE is a parameter in guide that controls the complexity of the tree that you want to have. If K is 0, the tree is complex. In fact, when K is 0, the tree is just this tree, the tree using the full data. When if your K is higher, then the tree is simpler. Okay, so let's see how you actually tune this parameter. Yeah, by default, the default parameter, the default value in the program is 0.5. Okay, so we want to try to understand how this thing actually works. Okay, so it's like this. So the first thing is you have to estimate the following. So this is the estimated misclassification cost, right? Cost of T, the tree. Okay. So for example, over here, once you build this tree, right, you can have a misclassification matrix like as follows. Let's say this is plus minus, right? So of course there is no penalty if you correctly predict. Let's say you have a penalty like this, right? So 1, 1. Okay, so this is equal penalty, yeah. So that means once you have this tree, you can estimate the misclassification cost by checking how many of these types of mistakes were done, right? So then you will have this RT, yeah, the misclassification cost for this tree. Okay. Now, once you have these 10 cross-validation trees, right? So each of them you can calculate their misclassification cost as well, right? So each of them will have its misclassification cost. Okay, so all right, so you have 10 of them, and then you basically calculate. So this SE of R hat T is basically the standard deviation of these values here, right? Okay, so you basically find the standard deviation of this set of cross-validated trees. Okay, so now suppose T star, right, minimizes this. Okay, so among here, right? So among these trees, right? Suppose there's one of them. Let's say this one, right? It minimizes so this tree makes this. It's just basically saying that one of these tree has a smallest misclassification cost. Okay. So after that, you will pick this tree. So you pick the tree with the following star plus KSE. Okay. K times the SE of R hat T. All right. So you pick the tree, so that has the that's within this that has the misclassification cost within this bound. All right. So let me just show this. Whose microphone is on? Can you just turn it off? Just a minute. Okay, share this one. Okay, so this is basically the KSE rule, right? So basically you have, so these are the trees, right? So this is the main tree. It's grown using all the data, and then these are your cross-validated trees, okay? So all of them will be slightly different. And basically you, okay? So let R hat T be the estimated misclassification cost of T, and let SE of this be the standard deviation, okay, of the cross-validation estimates for T. So basically, you basically find the misclassification cost for all these cross-validated trees, and you'll find their standard deviation, okay? So let subtree T star minimize this, okay? So that means one of these trees, right, will actually minimize, okay, one of them. So you'll find that one. Okay, so the KSE tree that is the smallest subtree such that this is true. Okay, so then you basically plug in. So you once you know that, so this is the minimum misclassification cost, right, among the subtrees. Then you plus, okay, this part here, yeah. Okay. So then this K is a parameter that you control. Okay, so you basically, the default is 0.5, all right? So then your T double star tree is basically the smallest subtree such that this is true. Okay, so basically when you add a value here, right? So basically you allow the misclassification cost to be slightly larger. Okay, when the misclassification cost is larger, right, that means your tree basically will be simpler, because a simpler tree will make more mistakes. Okay, but then a simpler tree is also more generalizable than a complicated tree, right? A complicated tree can fit overfit very easily. Okay, so this parameter K here will control the complexity of the tree, right? So if you want if you set your K to be 0, then basically your tree here, right, the cost is basically the misclassification cost is equal to the misclassification cost of the smallest, so the subtree T star. So basically it is, if you set it to be 0, it will pick one of these CV trees, yeah, with the smallest misclassification cost as the result. Okay, so basically meaning that you will pick the most complex tree among these cross-validated trees, right? Because the most complex tree usually is the one that fits better. Okay, so if you put K equals to 0, sometimes you need to put K equals to 0 in order to get some model that is with some reasonable amount of detail, because sometimes you put default 0.5, you only get a tree stump. Yeah, basically it's just a node. There's no splits, whatever. So in that case, maybe then you have to reduce your K, right? So that you get something, some results. So this parameter is an important parameter to tune in the guide program. Okay, so let me just, so basically then that's about the things that I want to talk regarding the theory part, okay? When you use guide for classification. So maybe we just look at some examples for regression. Let me check some results for regression, yeah. Okay, so this is an example of a, okay, so this is an example of guide producing a linear regression tree, okay? So these are the splits, yeah, okay? And you can see that these are the values, all right? So these are the threshold values, okay? And over here, you basically have, these are the terminal nodes, right? So the terminal nodes show a simple linear regression model with this variable of the response. So the response is some variable called MEDV, and the predictor is a variable called LStat in all these cases, yeah? And so this one is the, this is the model. Okay, so these are all simple models, okay? So you can actually visualize that, yeah? You can see that, okay, for this partition, okay, for this particular partition, the regression line, the regression model looks like this, which is good, right? So this looks reasonable, fits reasonably well, similar with this one. So all of them are fitting very well. Okay, the simple linear models are predicting the response quite well in these partitions. Okay. Okay, so I think that's all I want to talk about for classification and regression tree, right? So now I want to show you how the software actually works. So I'm going to remotely control Cui Zhuang's computer, but I'm not sure whether I will hear that echo. So let me try this. It's because I have to do that because for some strange reason I cannot run guide on my MacBook. Okay, so I have to use another computer to do that. Let me see. So I have remote control. Let's see. Hi, can you hear me?
Yes, but a bit echo.
Yeah, there's echo, right? Zhuizhuang, can you off the sound on your side? Muted. Okay, you're muted already. Okay. Is it bad for everyone? Or are there suggestions how to avoid the echo?
Just wondering if you are using mic on the other end.
Are you using mic on the? Oh. Are you using mic on the?
Because it feels like the part of the sound is actually like you have a speaker here and then there's a mic on the other end. So it repeats or what?
Maybe switch off the volume, switch off the speaker.
Testing.
The echo is considered minimal to me. I'm not so sure about others.
Okay, I think we'll try to say less things. But everyone can see the screen. Can everyone see the screen?
I'm not so sure which string are you saying, but what I'm saying here is the guide piecewise two variable model. Oh, now I see your string, yes.
So is it clear?
To me, it's fine.
Yeah.
Okay, so this is a demonstration with breast cancer data set, right? Okay, so to use guide, you have to give it two things. The first one is the data set, which is the CSV file, or in the form of a text file. Okay, which is this one. The second input file is actually a text file. And the text file has a certain structure. So I'm going to show you how to prepare the input file, yeah? Okay, so I have created a text file containing the information in this as follows, yeah. So it has a .dsc extension, but basically it's just a text file. Okay. So I have to change a bit of things. Okay, so basically you will get this text file. The first row you put the name of the data set. The second row, NA, is the notation for missing values. The third row, you will typically write a 2 because your data, the first row of your data are the variables, and your data actually starts from the second row. So the first 3 rows are as follows. The Excel data file or the text data file. And then you have the missing value indicator. And the third row is actually the row where your data actually begins. Then the rest of them are basically the variables. Okay, and you have 3 parts. The first part is the index. The second part is the variable name. The third part is a description of the type of the variable. Okay, so N means numerical variable. C means categorical variable. And D means the dependent variable. For the complete list of variable types, you should check the manual for guide. If you don't want to use a variable, you put an X there. So obviously ID, we don't want to use that. So diagnosis is the dependent variable, so D. Okay, the rest of them are just basically in this, for this data set, they are all numerical variables. Okay, so you are done setting the DSC file. So is it clear to everyone?
Yes.
So basically, if your data set is not very large, you can actually just manually type in these things on the text file. For example, if you want to just play with the iris data set, then you don't have to do what I did just now. Okay, but then since you have 32 column variables, so if you're going to type them out, it will take like a while. And then you might actually make typing mistakes, right? So it's actually better to prepare the file in R and then just output it as a text file. Okay, so the instruction is actually quite easy to do. So you just need to create a data frame with the number indexing, the column names, and then basically you will just put in then a character that most of the variables have, right? And then you can later edit it manually in the text file. Okay, so we can now begin to run guide. Name of batch input file, you just create any new name, right? Model fitting. So we will do a single tree here. 2 for ensemble means if you're going to do random forest, so you pick 2. So we're doing classification. Okay. Here, for starters, I will just use default option. Okay, this is the part where you have to give it the DSC file, yeah? If you have done it correctly, guide will show you something like this. It actually checks the data set. Okay, and then it reports what it has read into its program, yeah? Okay, so from here we will, so most of the time if you don't know what choice to use, you can follow the default. In this case, we will just say they are equal priors, all right? Which means you are assuming that benign and malignant cases are equally likely. So by default, your misclassification cost here will be equal. Okay, so 1 is for unit misclassification means the penalty is only 1. Okay, so you can, the final figure that is given is actually a latex tree. Okay, the program has finished running. In the okay, by default the number of cross validation trees is 10, yeah. Okay, the final tree that is returned here has 7 terminal nodes. you can basically look at the result very quickly by typing the output file. Okay, never mind. You can basically just go to the folder. You have the out file here, so you can actually double click. No, you just open with a notepad. Okay, so so this is the text file. It will show you the result of running. Okay, you have the guide version. So basically, you can, I'll just go through this. So these are the outputs from the program, but you just basically focus on the following things. So here you can see that this is the tree, right? This is a tree with the nodes, and then it will tell you what variables were used for splitting. Okay, so this is in a text form. So these details will not be very. It's a bit too much, and it will saturate you. Okay, so basically we don't read this. And we focus on the final result here. So this is the result of the classification matrix where you have the predicted and the true class, right? So here you can see that the number of, so the number of cases used 569, 16 misclassified. So you can see how they are misclassified. Okay. And that's it. So it only took like 3 seconds to run the program. Okay, so now we want to look at how the tree looks like, right? So for this, you will have to have the text. Cui Zhuang, can you bring me to the text? Okay. So, okay, if you, I find that the easiest way to visualize this is to create an account in the website called Overleaf. And basically, you just need to open the text file. And then you copy everything. Where is the overleaf page again? Yeah. Okay. Paste. We'll try to run it first. So you have to change this to, I think, XE, the text, the compiler. Then rerun. Okay, done. So you can see that this is the tree. Okay, so you can see that the caption here provides very clear description of how like some details about the tree parameters, like you're using 0.5 SE. Okay, and these abbreviations for V1, V2, V3, V4 are given here, right? Because these variable names are too long to be printed on the figure. So you can see here that it says predicted classes and sample sizes printed below terminal nodes. Class sample proportion for diagnosis equals to M beside nodes. So for example, like this node 4, right? 0.01 means there is 1% of malignant cases in this node. Okay. But most of them are predicted as benign. So you can see, so the yellow is for benign and the malignant is for green. Okay. So from here you can basically see that it's very transparent, right? How what features actually cause it to move around, like splits, yeah? So basically the variables use concave points mean, concave points worse, perimeter worse, fractal dimension worse. Okay. So if you feel like this, tree is still a little bit complicated, then you can tune the SE parameter. Okay, you don't actually have to rerun the whole program. You just need to open the input file, this bc.in, and then edit the parameter values. So for example, this parameter 0.5 here. Maybe you can change it to 1. Okay, then you save. And then basically you just rerun. Okay, you can use the up arrow and it will recycle the command. Okay, so now you get a model that is actually simpler. Okay, so your variables, you basically are just working with radius worst, concave points mean, V2, sorry, that's V1, and then concave points worst. Now, in fact, you notice that this split here is actually not so important because it's only dealing with 24 samples, right? So in fact, it seems like your model, right, a really simple model would just work with radius worst and concave points mean. So that two variable model, I think we sort of like also have covered, look at it in the case of SVM and some other simpler examples, right? Okay, so what happens is that if we use this simpler model, then our number of misclassified cases is actually more. But of course, the plus side would be that we might have avoided overfitting. Okay, so that's the demonstration that I wanted to show you. Okay, so I think, okay, so I've already quit the team viewer, so there should be no echo now. Okay, was it clear to you how to run guide based on the demo just now?
I think yes, just need to read a bit on the manual and documentation as well, I guess.
Yeah, actually running it is actually quite simple. You just need to prepare the DSC file properly. And after that, it's just, if you go by default, if you want more control, of course, you can choose not to use the default options, okay? Then there will be more options for you to tune, right? You can actually refer to the manual. The manual is actually very well written, so you can actually use it to see how it is. They have some test data sets there which you can actually use to run some of the programs. Run some of the examples. Then after you play with one or two examples, you should be able to use it for your own work. Okay, it's not a complicated program to use. Okay? But there is a very powerful program, so you may take some regular application for you to become to kind of like more appreciate its usefulness. Okay. In fact, one of the very good thing about this program is that you can basically write a script, yeah, and repeatedly call this program to run. All right. So if you want to do simulations and things like that, this program is very useful. Okay, you can repeatedly call it to execute certain tasks, yeah, and then you can collect the outputs and then do some analysis on the outputs. Okay. Okay, so that is the demonstration about Guide. So now, so I have to say something about the continuous assessment tool, right? So we will continue with the same groups, okay? Let me see if the spectrum is on. Spectrum has some problems today.
I think since yesterday, actually.
Yeah, okay, it's kind of like broken. Okay, never mind. So for the continuous assessment, what I would like you to do is to continue with the project, right? Continue with the data set that you have been working on. Oh, actually, it can access already. Okay. Okay, so these are the data sets, right? Okay, can you see my screen?
Yes.
Okay, so what happens now is that you use it, you use the data sets, and you now you use the classification, yeah? You use supervised learning to build a model for predicting the class labels, okay? So in this case, you don't actually need to, you just need to pick a particular model, a particular classifier, and then work on that, right? So there's no need to actually use, like, do several classifiers and then evaluate and pick one of them. So we'll just skip that, right? Usually you need to do that, but since there's not much time, so basically I'm quite happy if you know how to execute one of the classifiers and then derive some useful conclusions from it, okay? So yeah, so what happens here is that you pick, so for each of the 4 groups, the 4 data sets, you will decide, so how many groups do we have? 1, 2, so 2, 4, 6, 7 groups, is it? The diabetes group all merged into one, right? I think each data set has got two groups, isn't it?
Yes, and then yeah, the diabetes data set, they match into one group. Yes.
So So basically we've got 7 groups, all right? So now I want to maybe just yeah, so basically you will have to, so based on whatever you found in the previous, in the first part, okay, now you will build a machine learning model to actually make predictions, right? So you can choose which model you want to use, okay? But then should we decide the model now? I don't know. So that we have a variety. So that you know, sometimes if I let you go on and do all the models, then everyone is doing the same model. Okay, then the idea here is that we do a range of models, and then everyone can see the diversity of approaches being used, right? And then yeah, that will be something, right? So okay, so the class data set, okay. There are 2 groups. Can the group members just briefly identify themselves? The first group that worked with the glass data.
Yeah.
Chao Hong, right?
Yeah, yeah.
Yeah, your group. Okay, and whose group?
I think Wei Kyok Hua then.
Oh, you have one group.
I mean the other group. My group is Daniel.
Alex, right. Okay. Who are your members?
Si Kim and Alex.
Okay, I remember now. Okay. So for this data set, what model do you want to use?
I think I'll go with trees.
Huh?
Go with trees.
You want to use trees?
Yeah.
Trees.
Okay. Ensemble.
If you want to use tree, then you use guide lah.
Okay.
Guide.
Okay.
If you are interested in, you can actually compare the trees that come out from the other programs.
Okay.
RPart and yeah, since you're doing tree, you might as well you know, just do a comparison so that we can see like what are the differences. Yeah.
Okay. Okay.
Trees, and then so Wei, Kyok Hua, and is it Meng Yuan? Sun Meng Yuan, right? You're in one group, right?
Yes.
Yeah. So what model do you want to apply on this data set? What do you think? Pick one of the models. Kyok Hua, Wei, any ideas? Or Meng Yuan, what's your idea? Sun Meng Yuan, what's your idea? Yeah, any ideas? Okay, never mind, I'll come back to that group. So the diabetes group, Ruby, right? Ruby,
Yes, doctor.
yeah, and then who else is in the group?
Farhana, Suchi, Aida, and Chao Ziyun.
Okay. So what model do you want to? Okay, I think diabetes because it's 0, 1. It's so I think it's best you do the 3 lah.
Okay, doctor.
Just do the 3. Otherwise it's actually a little bit complicated. You have to do. It's got missing values, right? Has it got?
Oh, no missing.
No, it's missing.
No missing values. Okay. Anyway, just do 3s. I think this is the best model already for. I mean, in terms of ease and transparency. Okay, just do the 3. Then the hepatitis C.
Yes, doctor. Yep. And also, who else? Yeah, I think Hep C also suitable for 3. So.
3 again.
Yeah, of course I can do logistic regression as well. I mean, it's like not hard to do. Yeah.
You want to do SVM?
I'm okay with it.
This C has got mixture of variables, isn't it? Has it got mixtures or?
There's one categorical variable, which is the gender, if I'm not mistaken. Other than that, all is numerical variables.
A gender, is it considered an explanatory variable or is it just a metadata?
I doubt it because it's like, I think that there's some small variation between males and females for those other characteristic, the measurements part, but then it's not really too huge that we should, I mean, too huge that we need to look into.
Yeah, I mean, like gender aside, probably you can just, so then all the variables are numerical, so basically all the other methods can apply.
Yep.
Well, you want to try 3s? Just go ahead lah. Your group.
Okay.
Who's the other group for hepatitis C?
My group, Wei Silu, Wen Feng, and Qian Yi.
Okay. What model would you like to try?
ANN is good. Can we do ANN or?
You want to do ANN? Artificial neural network.
Yeah.
Okay. Okay. So you tune the model parameter. I mean, like you do the architecture and things like that. Well, let's see if you can beat the 3. Okay. All right. So yeah. So one of the hepatitis groups will do ANN. So we have one ANN there. 1, 2, 3. Then for the mice protein.
Hello.
Yeah.
Maybe for our group, my group member is Hinjun and Hafiz.
Yeah.
And can we try SVM?
Or do SVM? Okay.
Yeah.
You try SVM.
Okay.
Then the other group, want to do naive base. Probabilistic. Where's the other group doing mice protein? Which group?
Yeah, I think fine, doctor.
Jeff.
Yeah, Jeff. Yeah.
I'll do naive base.
Sure.
And just do a naive Bayes and see how close it gets to SVM, right? So of course, in the group that does SVM, you might have to try some kernels, yeah, and figure out like which kernel is the one that is better, yeah. Okay, because SVM has many possibilities with different kernels, right?
And also, yeah, doctor, I just wonder if our HEPC dataset can change to SVM, since I think there's some requests by group mates. Yeah.
Oh, do SVM can also.
Yeah.
If you do SVM, then your gender, I think you can maybe you can drop it because
yeah.
I don't know. It seems like very strange to say that
gender will affect.
Yeah. You just because you're a guy, you have a chance of getting hepatitis C more likely or whatever. So I think that is a big question mark, because even though the data might show that, but you have to always remember that the data set is observational data, and there could be some kind of a bias that's driving that. So because it's definitely very strange, right? You know, why would a particular gender be more susceptible to it? Yeah. So maybe you could actually drop that variable, the sex variable, and then just work with the others.
Okay.
That'd be also interesting to have a look. Because SVM is actually quite diverse as well. Okay, because we already have quite a few tree methods already. Yeah. And then the last one, the glass group, Hua, Bi Wei, and Meng Yuan. You want to say something? What model you want to use?
Yes, doctor, can you hear me?
Yeah, Amy.
Yeah, I'm Amy. Our group, just now we talk about the class dataset. Maybe we want to try use support vector machine.
Okay. Also SVM. Okay.
Yes.
Yeah.
Thanks, doctor.
Okay, great. So basically, what you do in this second part is you basically build a prediction model, and for this you have to do proper training and testing. Okay, so you have to reserve a testing set, right? That's not involved in the training. For you to use that test set to actually evaluate the performance of your model. Okay, so then you have to kind of like you have to partition your data randomly. Yeah. Okay. You can read up on some literature about that. Usually people may reserve depending on how much data you have, right? There's no hard rule. Maybe you can reserve some commonly used ratio would be use 70% to train, 30% to test. In some cases, you use 60% to train, 40% to test. So it will depend on if you actually don't have a lot of samples, then you might actually need to allocate more samples for testing, right? Because otherwise you would use all your samples for training and then you don't have many for testing, okay? So then even you test, if your test set is actually too small, then there's no point, right? Okay, so you have to, on the other hand, if your data is a lot, then you may actually, you can actually use something like 80-20, that's also fine, right? So you have to decide, okay, something reasonable. And then after you have done that, then make a recommendation, right? What are the variables that are driving the prediction, okay? And then highlight these variables and then make some kind of recommendation, okay? So, so for this, you have to, so we will have two parts, all right? One is your individual report, all right? The other one is the, again, like last time, like a group presentation, okay? So there will be like a group presentation, all right, where your group will talk about what you have found together. And then there's a personal report, yeah? Everybody in the group has to write in your own, of course, the results you will share it, right? But then, of course, the way you talk about it will be individual, okay? So then that report should be something like, maybe not too long also, yeah, I will have to cap it like maybe to about 5 pages, right? So that you just report things that are important, right? Otherwise, you may keep on adding too many irrelevant stuff and then you will lose the focus, right? Just about 5 pages, all right? And you don't need to do a fancy front page. Just straight away on the first page already give the problem description and then methodology and then your results and your discussion and your recommendations, okay? And with suitable figures put in, right? Put in good quality figures and then that should complete the report, right? Okay, so so this is week 12. So maybe we will look at this on week 14. Okay. Yeah, actually deploying the model is actually quite straightforward, right? It won't take you a lot of time. It's just thinking about how to interpret the model and yeah, that will maybe the discussion, all that you might have to do some literature search. But actually deploying the model, I think with the codes given, it should not be too, it's probably quite straightforward, right? You just maybe need to tune some parameters and that's that, okay? Okay, are there any questions you want to ask about this? This assignment. So later I will actually write down things in Spectrum so that you have something more concrete to refer to, all right?
Yeah, I'm about to ask this, then I got no more question. Thank you.
Okay. Yeah, I mean, I'll just write it down so that it's easier for you to check back. Okay. So, okay, so I've taken extra time, so I think I will stop now. Let me see, since Spectrum is on, so I'm just going to add the attendance there now, and then you can actually go and I'll just leave it on until 10:30, right? So then you can actually go and sign in yourself there. Okay.
Okay. Thank you, Dr. Khan.
Okay.
Okay, thanks everyone. So okay, let me put this. Okay, so you just go and sign your attendance there. Okay. Okay, that's all, everyone. So so good night.